We have seen that once we choose a basis, we can represent operators as square matrices, kets as column matrices, and bras as row matrices. The next question is, how do we go from one basis to another? We have already seen that basis is not unique. The choice of basis is not unique. How do we go from one basis to another, right? So we say that there's a transformation operator to go from one basis to another, and that's what we'll be discussing in this class. Suppose we have two incompatible observables A and B, then the ket space can be viewed as being spanned by either the set ket A prime or by the set ket B prime. Okay, ket A prime is the set of eigenkets of observable A which forms a basis, and set ket B prime is a set of eigenkets of observable B which also forms a basis. Right, so you can think of the ket space as being spanned either by this set or by this set. Okay, so we have here we see that if we have two incompatible observables, then we have two separate set of base vectors. The choice of basis is not unique. Now, as an example, we can talk about the spin half systems. We can either use ket Sx plus, ket Sx minus as the base vectors. This is a two-dimensional space, so we can use either ket Sx plus and ket Sx minus as a set of basis vectors, okay, or as the basis. What are these? These are the eigenkets of observable S. So Sx, right? Or you can choose the eigenkets of observable Z, which are denoted as ket plus and ket minus. Right? So we see that we could either choose this set as basis vectors or this set as the basis vectors or as base kets. Now the two different set of base kets span the same ket space. We are still talking about the same ket space. We are just using different basis vectors, different base kets. We are interested in finding out how the two descriptions are related. Now we are familiar with such kind of things from usual Euclidean vector space. All right. For example, in a two-dimensional Euclidean vector space, we could choose these two directions as I hat and j hat. Okay. Or we could use two other orthogonal vectors as the basis set. Let's say I prime and j prime. Right. So we are still spanning the same, we are still talking about the same two-dimensional space. We are just using different set of base vectors, all right, different set of basis vectors, and we know that these two descriptions will be related by a rotation matrix, right? We could what do you say, we could decompose any vector in the basis ij or in the basis I prime comma j prime, right? And when you go from one description to other, the components of the vector will change, and we know that these are related by a rotation matrix. All right, similar things happen here. Similar things can be shown to work here also. Okay, so changing the set of base kets is referred to as a change of basis or a change of representation. So if I use a particular set, particular basis, I say that this is the representation. This, we can call this a representation, and this another representation. All right. So when we change the base kets, we are changing the representation. So the idea is that we are talking about the same physical objects, but we are just using different representations. Okay. The basis in which the base eigenkets are given by ket A prime is called the A representation sometimes, or sometimes the A diagonal representation, right? We can call it as the A representation or A diagonal representation. What do we mean by A diagonal representation? We mean that in this basis, the observable A is represented by a diagonal matrix. All right, in this representation, we have seen that the observable A will be a diagonal matrix. All right, so you can either call this representation as the A representation or the A diagonal representation, in the sense that we are talking about a representation in which the matrix representation of A is diagonal. Okay. Now our task is to construct a transformation operator that connects the old orthonormal set ket A prime and the new orthonormal set ket B prime, the old basis and the new basis. All right, so we need a transformation operator that connects these two descriptions. Okay, so we start with the theorem. Actually, we start with the theorem. Given two sets of base kets, satisfying orthonormality and completeness, right? So we are talking about an orthonormal set of base kets which forms a complete set. Okay, so if we talk about two sets of such base gates, then there exists a unitary operator U such that B1 can be written as U acting on A1, B2 can be written as U acting on A2, etc. Alright, so the theorem is that there exists a unitary operator that connects these base gates. Okay. Let's now prove the theorem. Right. So we need to prove two things. One thing is that we have to prove that such an operator actually exists, and we have to show that this operator will be unitary. All right. By a unitary operator, we mean that U is a unitary operator if U dagger U is equal to U dagger is equal to the identity operator. Okay, if U dagger U is equal to U dagger is the identity operator, then we say that U is a unitary operator. All right, we can also say, in other words, we can say that if U dagger is equal to U inverse, okay, the same thing. All right, so U dagger here is U inverse. Okay, then U inverse U is the identity operator. So U dagger is equal to U inverse is the condition for an operator to be unitary. Okay. So we'll show two things. First thing is that such an operator exists, and secondly that this operator is actually unitary. Okay. So this is what we mean by a unitary operator. U dagger U is 1 or U dagger is 1. It's not 1, it's the identity operator. Okay. So we prove this theorem by explicit construction. So what's the best way to prove this? To actually construct such an operator. So if we construct such an operator that takes get from the old set, right, to a get from the new set. Okay, if we construct such an operator, that means that it has to exist. So we prove this theorem by explicit construction. Okay, and I think it's easy to guess this construction. We can write U is equal to sum over K get Bk bra Ak. All right. Now we can actually check if this condition is being satisfied. Right. We can check if this condition is being satisfied. Okay. Let's check this. So let's act this operator U on a ket AL, and we have defined the operator U like that. Okay. So U acting on ket AL is equal to, instead of U, I have this operator sum over K ket Bk bra Ak. All right. This operator acting on AL. Now we said that we are talking about an orthonormal set of base kets. Okay, so this is sum over K. Ket Bk, what is this? This is the inner product bra Ak ket Al. So by orthonormality, this is delta Kl. Now if I sum over K, there's a delta Kl here. Only term that survives is the term for which K is equal to L. Right, so I get Bl, ket Bl. Right, sorry, I missed this ket here. So this is ket Bl. Right. So we actually found the operator that takes ket AL to ket BL. Right. So if we can construct such an operator, we have proven that the operator exists. Okay. We have proved that the operator exists. Okay. Now we can show that we have to show that this is actually unitary. We need to check for unitarity. All right. So we need to check whether this operator that we constructed like this, sum over K, Bk Ak, right, Ak. This is the operator that we constructed. We need to check whether this is unitary. Okay, so we need to show that U dagger U is U dagger is the identity operator. So let's first write down U dagger. Okay, so I'll use a different dummy index other than K. Okay, I'll use a different dummy index L. Now I know how to find the dagger of this operator. So this bra Ak will become ket Ak, or in this case I'm using the dummy index L. So this bra A will become ket A, and I'll write it first. Okay, so this becomes ket AL, and this ket will become a bra BL. Okay, we know this rule. Okay, now we can find U dagger U. We just multiply these two terms. I'll write the summations together: sum over L, sum over K. All right, and you just write U dagger terms from U dagger first. It's ket AL bra BL. Okay, ket AL bra BL, and you combine it with U using the associative axiom. I can write this as ket BK bra AK. All right. Now we said that we stated the theorem for an orthonormal set, which means that this inner product is delta LK. Okay, this can be written as sum over L, sum over K, ket AL, delta LK, bra AK. Okay. Now I can carry out one of the summations. Let's carry out the sum over K. So if I carry out the sum over K, we see that the only non-zero value appears when K is equal to L. Alright. So if I carry out the summation over A, for K equal to L, this term will be 1. So I have to put K equal to L here, and all other terms are 0. So that summation will disappear. So this is sum over L, ket AL, bra AL. Alright, because in the whole summation, the only term that survived was the one for which K was equal to L. Alright, now by completeness relation, this is equal to the identity operator. We said that we are talking about an orthonormal set of base kits which obeys orthonormality and completeness relations, all right, which is an orthonormal set as well as which is complete. Now by completeness relation, this is equal to the identity operator. We have shown that u dagger u is equal to the identity operator. Now I leave it as an exercise for you to find u dagger is also equal to the identity operator. All right, so please try this. Just follow the same kind of steps and see if you get the result. All right, so both these conditions should be satisfied if you want to call u as a unitary operator. Okay, we found the transformation operator quite easily. We said that the operator u, operator of the form u is equal to sum over L, ket BL, bra AL. Right, an operator of this form will do the job. It will take a ket from the old set, ket A prime. Okay, this is the old set, and it will take it to another ket in the new set, in the new basis, in the new set of base kets. All right, so it takes a vector from here and changes it into a vector in this set. All right. Now let's look at the matrix representation of the U operator. So when we say the matrix representation of the U operator or any operator, we have to say in which basis. So let's find the matrix representation of the U operator in the set ket A prime or the old basis. Okay, let's find the transformation matrix. This matrix that represents the operator U will be called the transformation matrix. Let's look at it in the old basis. Okay. Now we know how to find the matrix elements. Let me write it like this. The ijth matrix element of operator U, the ijth matrix element of operator U can be written as bra ai, okay, U ket aj. Right? This is how we define the matrix elements. Now we just substitute this U from here in here. Okay, so this is equal to bra ai. Right? The summation over L, let me write outside, sum over L. So this is bra ai, and U is ket BL, bra AL, okay, and here I have got ket AJ. And again, since we are talking about an orthonormal set, this is delta LJ, this is equal to delta LJ. So this becomes sum over L, bra AI, ket BL, right, and delta LJ. Again, you sum over L. By now we are experts in summing over with when there's a Kronecker delta. So let's sum over L, and this becomes bra AI ket Bj. Okay. In other words, the ijth matrix element of operator U is bra AI ket Bj. All right. So this is how we have written it here. The kth matrix element of operator U. Okay. The kth matrix element. Here I have written Ij. Here I have written Ij, that's all. All right, I have written Ij. Here we are writing K and L, that's all. And AKUAL is obtained in this form. All right, it is bra AK ket BL. Right, these are matrix elements. So we combine, you combine each. So let's say that you take the first ket from this set and combine it with a ket from this set, and you'll get one element of this transformation matrix. All right, like that we can construct all the elements, and clearly this is an n by n matrix, a square matrix. Okay, in other words, the matrix elements of the U operator are built up of the inner products of the old base bras and the new base kets. Okay, so we construct this matrix. We can construct this matrix by taking the inner product between the base bras in the old set and the base kets in the new set. That's it. These are the matrix elements. Okay. some of you might have immediately realized that this looks like the rotation matrix in 3 dimensions that changes one set of unit base vectors into another set. Okay, I think we discussed these things when we talked about rigid body dynamics, when we are talking about rotations over there, and we said that we can write the new base vectors, right, in terms of the old base vectors, and we'll use the direction cosines to write them. Okay, I think we called these elements as the direction cosines. We would write this as cos theta 1 1, for example. Okay, so we had a notation for these things. Right, we called them as direction cosines. Okay. So it's exactly the same thing. All right, you see that this matrix is constructed out of the inner product, all right, or the dot product between the base vectors uh, from each set. Okay, one from the old set and one from the new set. Right, so I think this is the new set here. One from the old set and one from the new set. Again, one from the old and another one from the new. Right, and we construct these inner products or dot products, and we said that this is the rotation matrix. We saw that this is the rotation matrix. Okay, it's the same logic that works here also. So we have the transformation matrix, okay, with elements bra AK, ket BL. Right, one is the row index, other one will be the column index. Now the square matrix constructed like this is referred to as the transformation matrix from the ket A prime basis to the ket B prime basis. Okay, or we can say that from the A diagonal matrix, from the A diagonal representation to the B diagonal representation. Right, so we are going from a basis, a representation in which the matrix representation of A is diagonal to another basis in which the matrix representation of B is diagonal. Right, so we are talking about incompatible observables. This means that if A is diagonal in this basis, then B is not diagonal. Right, the matrix that represents B is not diagonal in this representation. Right, in this representation, matrix B is diagonal, but the matrix representation of observable B is diagonal, but the matrix representation of observable A is not diagonal. Okay, I think we have said that incompatible observables, all right, if the commutator is non-zero, they cannot be simultaneously diagonalized. All right, there's not one basis set in which both these observables can be diagonalized. Okay. Now we know that given an arbitrary ket, we can represent it in a basis by the expansion coefficients. We can write these expansion coefficients as a column matrix, and that can be considered a representation of ket alpha. Right? So we say that ket alpha can be represented by a column matrix with elements A1 alpha, etc., A2 alpha, etc. Okay. So given an arbitrary ket alpha whose expansion coefficients are known in the old basis, right? So the expansion coefficients is the representation of this ket, right? So these are the expansion coefficients. Now, once these expansion coefficients are known, all right, how can we find the expansion coefficients in the new basis, right? How can we find the expansion coefficients in the new basis, right? So the question is this: in the old basis, ket alpha will be represented by a column matrix with elements bra A1 ket alpha, bra A2 ket alpha, etc. Okay, all right. This is in the old basis. Now, in the new basis, the same ket will be represented by a different set of numbers because we have changed the basis. These numbers are bra B1 ket alpha, bra B2 ket alpha, etc. All right. Now, once we know these numbers, how do we find these numbers? That's the question. All right. Once we have this column matrix, how do we go to this column matrix? Now the answer is simple, right? What we need is this expansion coefficient. What we need is the expansion coefficients of alpha in the new set, right? So instead of prime, we are using K, L, etc. here to avoid confusion. What we need is the expansion coefficients of ket alpha in this basis, right? These expansion coefficients are nothing but bra bk ket alpha, right? This would be the elements of the column matrix that represents ket alpha in the new basis. Okay, what are these? These are the elements of the column matrix that represents ket alpha in the new basis. Okay, now we can insert an identity here in terms of the completeness relation, sum over L. Okay, get AL, bra AL is equal to the identity operator. Okay, so that's what I have inserted here. I have simply inserted sum over L, get AL, bra AL, which is nothing but the identity operator. I have inserted it in between here. All right. Now, what are these? These are the expansion coefficients of get alpha in the old basis. Right? These are the expansion coefficients of get alpha in the old basis. We can think of this as the elements of the column matrix that represents get alpha in the old basis. All right. So this matrix, okay, this square matrix actually takes you from the new, what do you say, the old representation to the new representation, from the old representation to the new representation. What is this matrix? All right. So if you look at this thing, we said that the matrix elements of U operator has this form, right? AL U AK. This has the form AL BK, right? So instead of AL BK, I have here BKAL. What I have here is BKAL. All right. Now, what is BKAL? BKAL is the complex conjugate of this thing. Right? BKAL is the complex conjugate of this thing. So let's take complex conjugate on both sides of this expression that we had earlier. This can be written as bra AL U get AK star. This is equal to BK AL, bra BK get AL. That's fine, right? Now, what is this thing? We know how to find the complex conjugate of the matrix elements like this. Let me write it here where we have space. Okay, what is this? We know how to take a complex conjugate of an expression like this. All right. So this will become, so this get AK will become a bra AK here. Right? Get AK will become a bra AK, and U will become a U dagger. An operator has to be replaced by the corresponding Hermitian conjugate. Okay, and this bra AL will become a get AL here. Okay, so we see bra AK U dagger AL is actually equal to bra BK get AL. This is equal to bra BK get AL. Right. So long story short, this bra BK get AL is nothing but the matrix element of U dagger in the old basis. Right. This is the matrix elements of U dagger in the old basis. Right. Now we see that this is in the form of a matrix multiplication. You have got U dagger, the kth element of U dagger here, and we can write this as the elements of a column matrix with one index alpha L. Right, so these are the matrix elements of the column matrix in the old basis. This would be the matrix elements of the column matrix in the new, sorry, the matrix elements of get alpha in the new basis. All right, they are related by the matrix U dagger, the matrix representation of U dagger in the old basis. Okay, so in matrix notation, this equation states that the column matrix for get alpha in the new basis can be obtained just by applying the square matrix U dagger to the column matrix in the old basis. Okay, so new column matrix, right, the new column matrix, so the new representation of column matrix is equal to U dagger acting on the old column matrix. Right, so we have got a transformation equation to go from the old column matrix to the new column matrix, or the column matrix in the old basis to a column matrix in the new, from the column matrix from the old basis to the column matrix in the new basis. Okay, this is exactly how we did in the case of rotations in three-dimensional space also. Right, we had the components of a vector ax, ay, az. We had the components of the same vector in another basis ax prime, ay prime, az prime. We saw that this were related by a rotation matrix. Right, so the similar kind of logic works here also. Okay, so that's the transformation matrix. Let's now find the relationships between the old matrix elements and the new matrix elements. Okay. Now, these are the matrix elements of the observable or an operator. It need not be an observable. So let's just say an operator. So these are the matrix elements of operator X in the new basis. We know how to find the matrix elements. Okay. We need to relate this to the matrix elements in the old set. So in order to do this, this is quite easy if you know where to multiply with 1, right? You multiply, you insert an identity operator here, you insert an identity operator here also. All right. Now we insert the identity operator in terms of the completeness relation for the old set. Okay, completeness relation for the old basis. All right, so here I have a sum over m, bra am ket am. This is one identity operator. All right, this thing along with the summation is one identity operator, the completeness relation for the old set. Okay, this is one. I inserted an identity here. I insert another identity in here. This is sum over n, that summation is written here, and bra an ket an. Okay, the rest of, except for these two identity operators, okay, what I have is the same thing, bra bk x ket bl. All right, now what are these? These are nothing but the matrix elements of x in the old basis. These are the mnth matrix element in the mnth matrix element in the old basis of operator x. Okay, so these are the matrix elements in the old basis. And what is this? So if you look at this, we already had the matrix that represents U. Okay, the L-kth element is given by bra AL ket BK. All right, and the matrix that represents U dagger is given by bra BL ket AK. Okay, so what is this? This is bra BK ket AM. This is nothing but the matrix element of U dagger. This is the matrix element of U dagger in the old basis. So I can write this as bra AK U dagger ket AM, right, using this thing. Okay, why? Because this bra bk ket am is the matrix elements of U dagger in the old basis. This is U dagger, and the old bases are written as AK am. All right, bra AK U dagger ket am. And what is this? This is ANBL. It's of this form, right? ALBK. These are nothing but the matrix elements of U in the old basis. So we can write this as bra AN U ket AL. We have identified all this as matrices. Okay, so we have written this as a matrix multiplication now. Okay, so this is simply the well-known formula for similarity transformation. All right, so here we have got a matrix which you can call a U dagger. Here another matrix which we can call X, and here another matrix U. All right, now this is the formula for similarity transformation in matrix algebra. In matrix algebra, you might have used expressions like this. Okay, we can have two matrices related by similarity transformation. A prime is a square matrix. It's related to the matrix A by a similarity transformation. S inverse AS, like that. Okay, now we see that U dagger is U inverse because we are talking about unitary operators. Okay, this means that this is exactly the formula for a similarity transformation in matrix algebra. I hope you have some recollection of studying these similarity transformations and their properties, etc. So this is the relation between the old matrix elements and the new matrix elements. They are related by a similarity transformation. The old matrices are related to new matrices by a similarity transformation. The trace of an operator. So we know that the trace of a matrix, if you have a matrix like this, the trace of a matrix is the sum of the diagonal elements. Trace of a matrix is the sum of the diagonal elements. Okay, we can define the trace of an operator X, all right, as the sum of the diagonal elements of the matrix representation of X. All right, so if you want to find the trace of an operator X, first you write down the matrix representation of the operator and then sum the diagonal elements. Okay, so trace of X equal to sum over A prime. Here I am writing this operator in the basis A prime, in the A prime basis, or in the A basis, all right, or in the A representation. So trace of X, in order to find trace of X, I first write down the matrix elements, okay, and then you sum over the diagonal elements. All right, so in general, the matrix elements are bar A double prime X ket A prime. I take only the diagonal elements, so which means that if the row index and the same index, so if the row index is same as the column index, we are talking about the diagonal elements. So we take only the diagonal elements bar A prime X ket A prime. All right, this is one diagonal element. We have to sum over all the diagonal elements, and this will give you the trace of a matrix. All right, so the trace of an operator X is equal to the trace of its matrix representation, and the trace can be written as bra A prime X ket A prime, and we take each such element and sum over all A prime. We sum over all A prime, which means that you have to take all the diagonal elements and then add them up. That will give you the trace. Okay. Now, even though a particular set of base kits is used here, we have used a particular set of base kits, and you can ask, what if I use some other base kits? All right, and there's no problem, because if I use another base kit, the trace does not change. You'll see that the trace does not change. All right, you might have already guessed this, because in matrix algebra you might have seen that similarity transformation does not change the trace or the eigenvalues of a matrix. All right. So in the same way, here we see that even though a particular set of base kits is used in the definition, trace of X turns out to be independent of the representation. This we can show. Right? We can show that trace does not change when you go from one representation to another. Right? This is the reason why we can call this as the trace of X. We don't have to specifically say the trace of matrix, the trace of the matrix that represents operator X in a particular basis. No, you don't have to say this. It's simply say trace of X. It doesn't matter which basis you use to calculate this. It's always going to be the same. Right? Let's look at the proof. This is the trace of X in this is the trace of operator X in the A basis, right, or in the A representation. Okay. Now we need to find the trace of X in the B. We need to relate this to a trace of X in the B representation, and we know what to do by now. We just insert two identity operators in terms of the completeness relation of the new base kits. Okay, so basically you introduce two identity operators here of this form, right? Sum over B prime, get B prime, bra B prime. That's one identity operator, right? I'll use another identity operator again, right? Since I am using one dummy index here, I'll use another dummy index here. So this is sum over B prime, get B double prime, bra B double prime, right? Sorry, sum over B double prime, get B double prime, bra B double prime, right? I insert one in here, right? I insert another one in here, right? And the summations I have written together over here. So we have just inserted two identity operators here. That's all we have done. Okay. Now we see that this is a number, right? This is a number. This is also a number. So numbers can be moved around. Okay. And we can put this number in here. All right. So let me just look at this term. So if I put this number in here, what we get is, let me write it here. There's a sum over A prime, sum over B prime, sum over B double prime. Okay. Now I'm writing this number first. So this is bra B double prime, get A prime. Okay. And I'm writing this number second. I have got bra A prime, get B prime. Okay. And then I've got this matrix elements. B prime, X, B double prime. Okay. Now what is this here? Again, I have a completeness relation in terms of the old basis. There's a summation over A prime also. So if I sum this thing, if I carry out the summation over A prime, this simply will become the identity operator. This get A prime, bra A prime, summed over A prime is the identity operator, right? Get A prime, bra A prime, summed over A prime is the identity operator. So that will vanish, right? That goes. Okay. What do we have? What is left now? There's this bra B double prime from here. That's what I have written here, right? And there's this get B prime from here, this get B prime. Okay, that appears here. And what is left here is bra B prime X get B double prime. These are the matrix elements of X in the new basis. All right. Now what is this? By orthonormality, this is delta B prime B double prime. Okay. Now I can carry out the sum over B double prime. I can carry out the summation over B double prime. Maybe I should write it here. Okay. This can be written as sum over B prime, sum over B double prime, delta B double prime B prime, and I've got bra B prime X get B double prime. Now I carry out the sum over B double prime. We know how to do this. Kronecker delta will disappear, and wherever there's B double prime, you should put B prime. Okay. So the summation also will disappear along with the Kronecker delta. So this becomes sum over B prime, bra B prime X get B prime. What is this? This is nothing but the trace of the matrix representation of X in the B basis, right? So we started with the trace. We started with the trace of X. Let me put it like this. We started with the trace of the matrix that represents X in the A basis or in the A representation, right? And we have shown that this is equal to the trace of the matrix that represents X in the B basis. Okay, the trace remains unchanged when you go from one basis to another. Okay, that's what we have shown here, right? So trace X turns out to be independent of representation. So trace is something independent of representation. Okay. Now we can also prove these relations. All right. I'll do one of them and leave the rest of them as exercises. Okay. So trace of xy is equal to trace of yx. Let's prove this. Okay. What's the definition for trace of xy? This is equal to sum over a prime bra a prime, choosing a basis. Okay. Bra a prime xy get a prime. Okay. Now I can use an identity operator. This is sum over a prime, sum over a double prime, bra a prime, and I am introducing, x, and I am introducing an identity operator in between here. This becomes bra a double prime, get a double prime, bra a double prime, together with this sum over a double prime. This is the identity operator. Okay, then I have got y and get a prime. All right, now these are numbers, these are matrix elements, so I can write this number here. So this is sum over a prime, sum over a double prime. I write this number first, bra a double prime, y get a prime, and I have got bra a prime, x get a double prime. Okay. Now what I do is that I carry out the sum over a prime. I can carry out the sum over a prime. All right. So carrying out the sum over a prime, we can use this relation, sum over a prime. Get a prime, bra a prime is the identity operator. So the identity operator will reappear here, and I'll have sum over a double prime, bra a double prime, yx get a double prime. What is this? This is by definition. This is nothing but the trace of yx. So we have shown that trace of xy is actually trace of yx. Okay, to prove this, you could either introduce this identity operators, or you could actually use this relation, right? You could take this u dagger x as x. Instead of x, I can write u dagger x, and instead of y, I can write u. Okay, so it doesn't matter. Trace of xy is trace of yx. So trace of u dagger xu is equal to trace of u dagger xu, and u dagger is the identity operator. So this is also equal to trace of x. All right, and these two relations, all right, I leave it to you as an exercise. Just do this in, these are operators, all right. This get a prime, bra a double prime is an operator. This get b prime, bra a prime is another operator, all right. So you can find the trace of this by introducing the identity operators appropriately, all right, in terms of specific base gets. All right, so I leave that these things as exercises for you. Right. So with that, I'll conclude the discussion. Thank you.